based on SCHMITT trigger. Last time we completed it, and the SCHMITT trigger is nothing but the positive feedback device. Is it okay? In which we were taking feedback from the output terminal and feeding it to the non-inverting terminal. Is it okay? So we have seen the SCHMITT trigger in which we are applying the input at inverting terminal. Later we will see the non-inverting SCHMITT trigger. In the non-inverting SCHMITT trigger, we'll apply the input to the positive terminal of it, or I can say the non-inverting terminal. So let's start the session with problem based on SCHMITT trigger. Then we'll switch to the non-inverting SCHMITT trigger. Okay. Let me take the problem. Wait a minute. So this is the 2017 GATE 2017 problem. And only 1 marks problem. Okay. And the problem given is, let me draw the circuit. The problem given, this is the op amp. Okay. This is V out to this op amp. At this V in is given. This is the non-inverting terminal. Feedback 10K, 5K, and this is 3 volt battery connected over here, 3 volt. Okay, so everything is given like this in the form of circuit. Now the question is, the question says, for the operational amplifier circuit shown, the output saturation voltage are plus minus 15. Saturation voltage are given plus minus 15 volt. Okay. The upper and lower threshold voltages for the circuit respectively. He is asking VUTP, upper and lower. It's LTP. Okay. He's asking for the upper and lower threshold voltages. These are the threshold voltages over here. Okay. So the options are given. It's plus 5, minus 5, 5, minus 5. Option B is given 7 and minus 3. Option C is given 3 minus 7. And the last option is 3 and minus 3. So how to do it? So friends, you need to calculate the value over here first. Is it okay? What is the value over here? See, the value over here is, if let's take V0 is plus 15 plus V saturation. We know that in the SCHMITT trigger output can sustain 2 conditions only, whether it will be plus V saturation or minus V saturation. So we are assuming that here the voltage is 15 volt. It is the max. This is the op amp circuit and it does not take any current from the circuit. So this is your entire circuit. In this circuit, if this is 15, what current will flow over here? I will be 15 minus 3 divided by 15K, if I am right. 10K, 5K, they are in parallel. The potential difference is 15 minus 3. So definitely it will be 12 by 15 milli. Is it okay? This is your current. Now you find the current and I need the voltage over here. The voltage over here is the drop across 5K. Let's take it V5 plus this 3 volt. Is it okay? So total drop over here is 3 plus V5. Is it okay? This 3 and V5. Now what is V5? V5 is the current multiply with resistance. What is resistance? 5K, and current given in milli. Milli and K will cancel out. 5, 3 and 3, 4. So this is plus 7 volt. Plus 7 volt. So this is the upper threshold point or upper triggering point. UTP, I can say UTP, and this is 7 volt, means if your V in is greater than 7 volt. The condition says if your V in becomes greater than 7, then your plus V set will go to minus V set. So upper trigger point is 7. It's perfectly fine. It's clearly visible over here. If your V in is greater than 7, then your 15 will come to minus 15. At the negative terminal, the potential will be higher than positive terminal. So suddenly your output will change. Okay. Now let's take the lower point now. Okay. Let me erase some part over here. Then I'll proceed for lower trigger point. So friends, it's a very easy circuit, kind of, in 1 minute anyone can find. Okay, only 1 minute. So now they are asking for the lower point. So for the lower point, I have to consider minus V saturation. Okay, so let me consider minus V saturation. So minus V saturation. So now let's take your value of voltage is minus 15. So the minus 15, again you have to apply over here. You have to find the current, right? So current is minus 15, potential difference minus 3 divided by 15K. Is it okay? Equal to 0. So this is minus 18 divided by 15 milli. Okay, this is your current. Now you have to find out the voltage drop over here. Let's take the current direction is like that only, because we assume the current, but use this minus sign over there also. So the voltage, this voltage will be this 3 plus 5K into current in it. So current is 18 divided by 15, and this is milli, and this is K, 5K into 5K. Okay. So milli and K will cancel out. 5 3s are, and 3 6 times. So voltage is 3 minus 6 minus 3. So lower point, V lower threshold point should be minus 3. So your overall answer is 7 and minus 3. And instead of this, suppose they are asking what is the hysteresis width. So it will be 7 minus minus 3 equal to 10. Your answer should be 10. Why 10? Let me show you. The condition for the circuit is like, here I'm taking V0, here I'm taking Vi. Let me draw the output. This is V0 plus V saturation, and for this figure it's given 15 volt at 7 at Vi equal to 7. So here is the 7 volt. The plus V saturation is going to sudden at minus 15. So this is minus 15, no problem at all. And beyond minus 3, so this is minus 3. Beyond minus 3, the system is going minus 15 to plus 15. So this is the output of the SCHMITT trigger. Is it okay? The output is circulating like this. So what is this total width? This is the hysteresis width we call. So 7 on positive line, minus 3 on negative line, total 10 you have. So this is your hysteresis if they will ask. Okay. Now let's come to the non-inverting type of SCHMITT trigger. Okay, our next topic. SCHMITT trigger is over. This hysteresis width is over. Now we will switch to the next one. This is the non-inverting SCHMITT trigger. See, this is the circuit of non-inverting SCHMITT trigger in which we are applying the input to the non-inverting terminal. So figure is looking like, here is the V0. This terminal is grounded. Okay, the inverting terminal is grounded. Now everything is going to be at this terminal only. This is R2. Here I am connected with V in. Okay, and this is the positive feedback. So in the SCHMITT trigger, we always have the positive feedback only. Here is the voltage. Okay. Now, what will be the condition over here if situation is like this? If you can find out the voltage over here, and that voltage will be greater than 0 because this is the ground, right? If the voltage is greater than 0, I can say it will be go in plus V saturation. This voltage is greater than 0 means at positive terminal you are having higher potential, so you will be definitely at the output switch from minus V set to plus V set. But suppose this V, let's take it VO, let's take it VO, not VO because this is the output. Let's take it V itself. So V is greater than 0, so definitely your output will be plus V set. If your V is less than 0, so definitely your output will minus V set. So how it works, let's see over here. Under SCHMITT trigger, the voltages at which the output switches from plus V saturation to minus V saturation. So this is the SCHMITT trigger about they are talking, or vice versa, and call the upper trigger point UTP and lower trigger point LTP. So the difference between the two trigger points is called the hysteresis. We have seen about this. So this point is pretty clear to us. Now in the next, in this case again the feedback is given at the non-inverting terminal. In the previous case also the feedback is remain constant and it will be to positive terminal or non-inverting terminal only. The inverting terminal is grounded in this case and the input voltage is connected to the non-inverting input. See, over here we connected the input. The negative terminal or inverting terminal of the op-amp is grounded. Okay. And the input voltage is connected to non-inverting terminal. The figure shows a non-inverting SCHMITT trigger circuit. Here is the circuit. Now we'll see how this output we are drawing over here. So to analyze the circuit behavior, let us assume the output is negatively saturated. We assumed this. Okay. Let me show you. Wait. The SCHMITT trigger circuit is like this. And remember one thing, this is the non-inverting. The output we are taking over here, the inverting terminal of the op-amp is grounded, no problem at all. And this is the positive. Over here the situation is like the feedback resistor, let's take it R1. Over here let's take R2, and to this R2 I connected V in. Okay. Now everything is related to this coin. Let's take it VT. Is it okay? This is the circuit given for non-inverting SCHMITT trigger. Okay. Now we'll see how it's going to work. Okay. So friends, please observe it carefully. If this is the VT over here, this VT, apply the nodal analysis at this point. So it will be VT minus V in divided by the resistance is given over here R2, the potential difference R2, the current is over. Now here I have to take the current. It will be VT minus V0 divided by R1. This current is over. What about this current? This is zero current because we know op-amp takes zero current. So it's 0 equal to 0. Is it okay? Now, if you will see this, I need the value of VT individual. So I can compare VT with 0. So let's take VT. This is 1 by R1, 1 by R2, VT, and at this V in divided by R2 plus V0 divided by R1 will be here. Is it okay? So your VT is totally this. So I'm giving this B as the name and I'll take B that side. So it will be VT. This is the entire thing A. Let's take it A divided by B. Now condition is if VT is greater than 0. Two condition we have. VT less than 0, VT greater than 0. When VT will be greater than 0, this wall part go to this side and will be remain with VIN divided by R2 plus V0 divided by R1 equal to 0. Now what will be the equal to 0 or greater than 0? Okay. So what will be the relation between output and input by this circuit? Wait a minute, I'll show you. So it will be V naught by R1. The V naught by R1 is going to that side. So here I'll remain with V in by R2. Is it okay? So finally, we'll get the relation between V in and output is nothing but, let's take it greater than equal minus R2 by R1 of V naught. Is it okay? So this is the Vn condition given. If Vn is greater than this thing, then only what will happen? We'll get the plus V saturation. Plus V saturation. Why? Because if you remember, we consider the greater than condition. What this greater than condition says, that Vt is greater than 0. Here is the Vt. If this Vt is greater than 0, definitely your output will switch to plus V saturation. If your Vt will be less than 0, so definitely your output will be minus V saturation continuously. So based on Vt greater equal to 0, I come with this condition. I have the relation between V in and V output. So this condition belongs to Vt greater than 0, means a plus V saturation. Means this condition is there in the system, we are having in plus V saturation. Okay. And if I'll take the opposite of it, it will be, see friends, let me write over here. So I can write over here like, let me erase it. Here I'm taking V naught. Here I'm taking V in. Okay. Now, the condition is, when we'll be having plus V saturation? When we'll be having plus V saturation, we have seen the value of V in should be, it was like minus R2 by R1 we got there. Okay. Actually we got the condition that V naught is equal to minus R2 by R1. Let's take it like this. Okay. Now the question is, if V naught you considered plus V saturation. Now if this is plus V saturation, the next step of this will be minus V saturation. And when it will go to minus V saturation, you have seen the diagram. This is minus, this is plus, this is 0, and this is whatever input we are applying over here. Let's take Vt, and because of Vt relation greater than 0, Vt less than 0, we are having relation between V naught and V in. Now the condition is, for suppose you have V saturation and you want to go to minus V saturation, means you have to switch yourself V set to minus V set. The condition is your V in should be less than this. If your V in, by this relation I'm giving only, by this relation your V in should be, I think I write wrong over here, this is V in or V naught. This is the V in and V naught. So if this V in is lesser than this, then it will come to minus V saturation. Okay, if lesser than, and if V in is greater than this part, minus R2 by R1 into V naught, if it will be greater than this part, then definitely it will switch minus V set to plus V set. Is it clear to you? This is the condition first. See, this is the condition, please remember. Now what the condition is saying to you, condition is saying that if you have V in less than this, only two conditions we have. If Vn is less than minus R2 by R1 of V naught, then your output will be minus V saturation, we are saying. Okay. If they are saying that Vn is greater than minus R2 by R1 of V naught, it will be plus V saturation. Simple. Is it okay? Now let's see what's going on over here. So, what is the hysteresis with and what is the lower and upper point over here? Let's come over here. I'm doing it like this. Hysteresis. We'll see the hysteresis over here. Before that, what is the formula? The formula is minus R2 by R1 of V naught. Okay. The condition is Vn is greater than this. If Vn is greater than this, then it will be go minus Vset. If Vin less than this particular thing, means minus R2 by R1 of V0 will have plus V saturation. Plus V saturation. Okay. So when plus saturation will become, means initially the value of V0 will be minus V saturation. Let's talk about this condition. V0 is plus V saturation, right? And in this condition it will switch to minus V saturation. So it's kind of V in should be less than R2 R1 of this Vset. Is it okay? Minus of this. Correct? So this is the condition. Your output will come from plus Vset to minus Vset. So here is the point. Minus R2 by R1. R2 by R1 of something Vset. And your output is coming. So here direction is like this. Plus Vset to minus Vset it will come. And simply over here it will come R2 by R1. It will go to plus V saturation. Is it okay? So in the inverting, the direction of this was clockwise and here it's anti-clockwise. Okay? I hope it's clear. Now we'll see one gate problem based on this. Okay? So this is the 2004 problem and 2 marks problem. Gate 2004. 2 marks. And the problem given is, here is the op-amp taking output. The power supply is plus 10 minus 10. No problem. The negative terminal connected with ground. Fine. This is the non-inverting terminal. Obviously, we'll take feedback if it is non-inverting SCHMITT trigger. So this is the output is feedback to input 10K. Here it's 5K. And this is V in. V in. Now the question is the figure A. Actually, 2 figures are given over here. The waveform is also, output is also given over here. Let me draw the output. The output is simply, wait. The output is given in this way. Like this. Like this. And this. The direction is anti-clockwise. Obviously, it will be anti-clockwise because non-inverting we have. And this max given 10 volt. And here it's given minus 10 volt. And these are 2 points given over here. The points are VTH, and VTL. Means threshold points given. Okay. Upper threshold point and lower threshold point, and the question will be definitely they're asking for this two, VTL and VTH only. So the figure A show a SCHMITT trigger circuit and the figure B is the corresponding hysteresis characteristics. The values of VTL and VTH are, your options are given. First VTL is given and that is minus 3.75 and the next one is 375. Option B is also minus 1.5. Option C minus 5.1 and the last option is minus 5 and 5. So how to proceed it? We just calculated that V in. The relation is like, the relation between V in and output was minus R2 by R1. Minus R2 by R1 and this was V0. Okay. So for the lower point, if you want to calculate VTL, it will be here minus it is as it is R2 by R1 and this should be plus V saturation. Okay. Because plus V saturation will be there, then only it will go to lower saturation point. And this was R2, this was R1. So minus 10K divided by 5K and the saturation point is 10 itself. Okay. But in the circuit we have seen this was R1 and this was R2, right? So I have to change this. So VTL is minus R2. R2 is 5K divided by 10K into 10. Okay, so this is nothing but minus 5. Minus sign is also over here. So VTL you have find out minus 5. And at the same time, the VTH will be plus 5 because this is same in both cases. Okay, the formula is dependent on Vset and minus Vset only. And what are the circuit parameters? This is the ratio of R2 and R1. Okay, so for this we are getting minus 5 and 5. Do we have in the circuit and options? Yes, we have. So D is the answer. This was the 2 marks question. Is it okay, friends? So is it clear to you? What the formula you got over here? See, the formula for non-inverting, what you get is, and suppose you don't know formula, forget about this. You can solve this circuit by your own. How? Let me do for you. Wait a minute. No need to remember formulas because this is the simple circuit given and you know the circuit theory. You can apply over here and we'll get the answer. Okay, how? Let me solve in that way also. You assume that here is V saturation, means 10 voltage over here. Okay, friends. Now let's take it 0 itself. Why? Because we have to compare with 0 only. Okay, so let's take it 0. So it is 0 minus V in divided by 5K. Okay, and this will be 0 minus V naught, that is 10 divided by here 10K equal to 0. Okay, so if you will do the LCM for this, it will be 10K minus 2V in and it will be minus 10 equal to 0. So this V in you are getting over here, this 10K will go to this side, minus 5. You are getting minus 5 volt. Now tell me one thing now. If your V in, this V in is greater than this minus 5. Here this you are getting for minus, you consider plus saturation, right? You considered initially your V naught is plus saturation. V naught is plus saturation in this case. We assumed over here 0, means your V in should be minus 5. If your V in should go beyond minus 5, means this is minus 5, it will go minus 6, minus 7. Suddenly your output will change and will come minus 10. Is it okay? So this is minus 5 for the lower point, and for the upper point if you will calculate, you will get plus 5 over there. Is it okay? Means if your input now will cross this 5 volt, immediately your output will drop. So this is about SCHMITT triggers. Okay. So apart from this, the positive feedback we are using. See, this is the positive feedback. If you are providing positive feedback to your op-amp or comparator circuit, so for this, as application you are using in SCHMITT trigger. Okay, apart from this, a triangular waveform generator is also there. Triangular waveform generator. In this also, we are using this application of positive feedback. Okay. Now let's come to the next topic. So let's come to the next topic, and that is Miller circuit or Miller effect. What is the Miller effect actually? See, the circuit of Miller effect is like, this is V naught minus plus, this is grounded. You are applying input over here, and this is Z. Okay, the feedback impedance over here. Now, according to Miller effect, we are calculating the R equivalent of the circuit only. If you have the circuit in this way, what will be the R equivalent or R at the input stage you will get in the circuit? Okay, this is nothing but the Miller effect. So if I'll draw the equivalent circuit of this op-amp, so equivalent circuit of op-amp we have seen earlier, here this is minus VD, the difference between positive and negative terminal. Okay, and this is grounded. Actually the positive is grounded. This is the output stage. Here I am taking V0, and V0 is voltage source only, and the source is multiplying with VD difference. The output is V0 equal to AD into VD. Is it okay? And from output to input point, we have feedback Z also. So we connected Z. This is the equivalent. Here it's a Vin. This is the equivalent circuit. Now they are asking what is the R equivalent of this. R equivalent means at this input stage we applied the voltage is Vin. Now because of Vin, because of this Vin, suppose in the circuit the current is In. So you need to calculate ultimately Vin by In. Is it okay? Now let's see what is the In is going on over here. So I'll apply nodal analysis at this point. So this point the voltage is minus VD. So I'm going to start minus VD. First I'll take this branch. Here it's a minus A into, let's take the gain of this A. So this is A, VD divided by Z. No problem at all. And in this In is coming. Incoming current minus. So I'll take on opposite side. So it will become plus. Is it okay? Now what is the relation between VD and Vin? Both are same because Vin is this and this. So with negative relationship means VD equal to minus Vin we have. So this will become Vin minus, this will become minus Vin divided by Z of In. Is it okay to you? So the condition is I hope it's clear to you. Okay. So condition is Vin plus AVin divided by Z equal to In. Okay. So this is 1 plus AVin divided by Z equal to In. You need to calculate Vin by In. You will take this In this side and everything will go that side. So you will remain with Vi divided by II. In is nothing but Z divided by 1 plus A. This is the output of Miller circuit or Miller effect. So why we are studying this? See the impact of this circuit. If you have connected some impedance over here and to some signal you are providing this circuit, that signal is facing almost zero equivalent or zero resistor at the input stage. Why zero? Suppose you chosen over here only 100 ohm. Suppose let's take at the feedback you have chosen 100 ohm. If you have chosen over 100 ohm and for this entire circuit the R equivalent is Z by 1 plus A. So 100 divided by 1 plus A, and you know A is very high. A is infinity ideally in the op-amp. So your R equivalent is nothing but 0. R is nearly 0 means there will be no drop in the circuit. Is it okay? If some current is coming at this stage, there will be no drop in the circuit. The entire current will come to at output level. Is it okay? So this is the Miller effect. So without dropping anything or loss, we are getting whatever input we applied, we are getting at the output terminal. Okay. So practically this is not possible, but ideally it's true. See, suppose you see, if you have connected like this two resistors R1 and R2, and suppose you have some voltage over here Vin. So if you are adding resistances in the circuit in series combination, your current is going to decrease. Current will be same in the circuit, but it's going to decrease. Why? Because the current value is dependent on number of resistances also, or the value of resistance, I'll call it R2. If you are adding R3, R4, so your IN is going to reduce. Okay. So if you are adding circuits, resistors in the circuit R1, R2, R3. So at input stage initially suppose you have this circuit only, or initial your current is something like 2 ampere. Now if you are adding some elements into the circuit, so current is going to decrease. You are not getting the desired current. You want that 2 ampere should be everywhere. At this point also 2 ampere you want over here. But if you are adding the elements, it is going to decrease. Okay? Because battery is fixed. This voltage is fixed. You are changing the resistances, so definitely the current value will decrease. But due to Miller effect, what Miller effect says, there will be no drop. Miller effect or Miller circuit is saying that if you want to apply anything, please apply to me. Whatever you apply to me, I'll deliver at the output at full form, fully. See, if you are applying me IN, I'll deliver at the IN at the output stage also. If you are giving me VIN, I'll take this entire thing and we'll go over here. This is kind of application of Miller circuit. Okay friends, now we'll see the most important part, and that is negative feedback. Okay. The last topic of this unit is negative feedback. Earlier we discussed about the negative feedback in brief, but now we'll see the details of it. Okay. So what is the negative feedback? Wait a minute, I'm showing you. So in the negative feedback, if I'll talk about the general circuit, so general circuit is like, this is the gain of the system. I'm taking output over here. Okay, this is the input stage. Over here, you are applying X as your input. From the output, you are taking feedback. This is the feedback element, and you are giving to this stage with negative sign, negative feedback. So this is the input stage. At the input stage, we mix the signals. So this is the mixer. This is the mixer over here. At the output stage, we sample the signals. So this is sampler. The output is formed in two forms. One is feedback signal. What is output? One is output signals. Okay. So at the output stage, we call the sampler. The input stage, we call the mixer. Is it okay, friends? Now, if you will apply the control formula, or how to find out the transfer function of this, the transfer function will be definitely 1 upon 1 plus A beta. This is the transfer function for this circuit. Is it okay? For the negative feedback, over here, you will be having plus sign. Now in this condition, suppose A beta is very high than 1, greater than 1. In this case, I can neglect the 1, and your transfer function in this case will be 1 by beta only. Because A by A beta will remain with 1 by beta. This is your transfer function in the case of A beta is greater than, multiplication of A beta is greater than 1. Is it okay, friends? Now, in the negative feedback, last time we have seen some topologies also, or we have seen some circuits in which we have seen voltage control voltage source, current control current source, current control current source is done, current control voltage source, like this. 4 types of parameters we have seen. Okay. So we'll discuss about all of them here also. So before that, again I'll tell you, if you are having 4 types of amplifier, first of all I'm saying, and those are voltage control voltage source, voltage control current source, current control voltage source, current control current source. you have 4 types of amplifier only. Okay, and for all this amplifier, the input and output resistances are different. Okay, so earlier I told you, if at the input stage you have voltage control or current control, only 2 possibilities are there at the input stage. It may have, this is the current control. It may have voltage control or current control. At the output also we are having only 2 conditions, and 2 conditions are, it may be voltage source or current source. Okay, no other condition is existing over here. Now we have seen, if at the input stage you have voltage control or at the input stage you have voltage, R in will be infinity. If at the input stage you have current, R in should be 0. Okay, R in infinity means you need the maximum voltage. You are applying voltage to something, so the entire voltage should be there at those points. Okay, so when you are applying this V, suppose at this stage you are applying some V in at the point A and B. So when you will get the entire input output, when there will be no drop of the voltage. When the voltage will not drop, when this A and B will be open circuited. Open circuited means directly they have the entire voltage. So open circuit means R in is infinity. On the same time, if you want the current control, so in the current control, the entire current should become in the here in the system. So suppose current is coming to somewhere, so in between A and B you need entire current, because this is the input current, this is the system part. Inside of system, into this system you need the entire current whatever is coming. If you will take R is infinity, so no current will come into the system. So if you want to take maximum current, you need to do this R in short circuited, or you have to take 0. So in the case of 0, the entire current will come to the system only. So that's why we are choosing R in equal to 0. Similarly, at the output stage, if you have voltage source, it will be R0 is 0. If you have current source, R0 will be infinity. Why so? Let me show you. At the output stage, the circuit is like, see, at the output stage, this is R0 of the circuit, and here you have, like, it may be voltage source or it may be current source, like this. Here I'll apply the load RL. Now my task is, suppose you get over here current. Suppose you get current over here. Okay. So in the current source, the resistance should be always in parallel. So let's take it. It's a voltage source you got over here. Okay. Voltage source means you are getting AD of V in. This is amplified version. Now at the output stage you are getting V, that is the AD into V difference. Is it okay? So this is the voltage, and we know always the resistance is connected in series with voltage. Now what I am saying is, if you have voltage source, yes, I have voltage source, so you need R0 is infinity. So friends, this entire VS is my task is should appear on the load. Load means whatever you have, please give us. The load is saying, don't drop anything. But because of this R1, there will be voltage drop. We know in the series combination the voltage is dropped. So what should be the R0? So the entire VS should appear across this. It should be infinity. No, it should not be infinity. If it will be infinity, there is the open circuit. Nothing will go over here. So it should be short circuited. Short circuited means there should be 0 voltage drop over here in the system parameters. This R0 is related to the system. Okay, so entire output, if you get at the load stage, your R0 must be 0. That's why R0 we are taking 0. At the current source, for the current source, the R0 should be infinity. So please remember this. This concept is very important. Okay. Now my point is, this is the voltage control, voltage source, everything is clear to you people. Okay, now let me tell you one thing. If you have voltage control, voltage source, what will be the output and input resistances for them? If you have voltage control, voltage source, what will be at the input stage? Definitely it will be R in equal to infinity, and for voltage source R output is equal to 0. Okay friends, so earlier I told you when R is going to increase, we called it series. When R is going to decrease, we call it shunt. Is it okay? Shunt means parallel combination. Okay friends, so is it okay to you? Now let me come to different names of voltage control, voltage source. Voltage control, let me erase this part also. Voltage control, voltage source is nothing but series shunt topology or series shunt amplifier. The other name of this is, the input stage is, this is the input stage, this is the output stage. Here also I am taking input stage and output stage. And another way to write is also available, in that we'll take the output and input. But at the output I'll take the name of output. So let me show over here. Okay friends. So first I'll start with the voltage control, voltage source. Voltage control, voltage source. What is at the input? VC. VC means series. Why series? R is infinity. At the output VS. VS means shunt. Is it okay to you? Shunt means R is 0. Voltage source, if you remember that formula or that diagram, infinity, 0, 0, infinity, voltage, current, voltage, current. Okay, so voltage, 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 infinity, 0, series, shunt, series, shunt. Okay, we'll take another one. Voltage control, current source. So voltage is the series, current at the output is also series, so this is series, series. Now let's come current control, current source. At the input current, current is shunt. Current is shunt over here, and at the output current source, at the output current is series. Now let's come current control, voltage source. So current at the input is shunt. Current at the output is, voltage at the output is 0. So this is shunt, shunt. Okay friends, now let's come to this topology, or the name is given in this way also. First I'll take the output and I'll take the name of the output. Output is voltage, output is voltage, yeah. So here I'll write what is the output. At the output we are taking voltage, so I will write over here voltage, and here is the input. Input is series. In this way I'll write it, input series. This is the mixing kind of thing. I'm mixing these two. What about voltage control, current source? So at the output is current, because first is current, first preference is output. So this is current. Okay, current is okay. At the input stage you have series. So whatever you will take over here, it will come shunt. Over here it will come shunt, because this thing is coming to over here, and this is going to change. Here again at the output stage you have current. If you have current at the output stage, it will be, you will write over here current shunt. Okay. Now if you have, now let's come to this. At the output you have voltage. So you will write the voltage over here. So voltage shunt. I think all these are clear to you. Okay. in the earlier slides we have checked the connections also. If this is your input, let's take it A, and feedback elements, let's take B. To the input you are applying some input like this. Okay, and you are taking the same thing over here. So what is shunt at the output stage? The shunt is parallelly you will take this output to feedback also, like this. So at this stage this is shunt. If you don't want to tell it shunt, you can use voltage also. Because in the voltage source, if you remember that formula, voltage source has zero resistance. So this is the 0 ohm circuit or minimum resistance. R is minimum. R is very low. That's why it's a shunt. Shunt means parallel also. This is I call the parallel. Okay. Now this is the input stage. If input stage I'll take in series. So I'll take in series means like this will be series. Now your input will be in these 2 points, between these 2 points. This A and B, they are internally connected in series circuit. In the series, this is the series combination. Here you are applying V in, here you are taking V naught. So this is series and this is shunt. And what is the way to write in series and shunt form? You have to simply write series and shunt. Okay. So what is this shunt and series? Which one we assumed? At the output you need voltage source. At the input you need series. Series means voltage control. So you have voltage control voltage source. Okay. So at the output also voltage, input also voltage. So this is the voltage amplifier, voltage gain. At the output you are getting some voltage, you are applying some V in, you are getting voltage gain over here. So this is voltage amplifier. Is it okay, friends? Now for other circuits in which you have voltage control, current source. Now check. At the output you have current. At the input you have voltage. So this is conductance. So this is trans conductance amplifier. Trans conductance amplifier. Why trans? Trans means we are using current from second circuit and voltage from input circuits. So your relation is transferred. So I called it the not normal conductance. This is the trans conductance. Okay, amplifier. I will add over here the amplifier. Now if you have current control current source, current control current source, at the input you have shunt, or let's forget about it. This is nothing but current gain. At the output current, at the input current, this is the current gain circuit in which we'll get the current. Okay. And if you have current control voltage source, mean at the voltage, at the output stage you have voltage, at the input stage you have current I. So this is simple resistor. Okay, friends. So this is we not call the resistance amplifier. This is trans resistance. Again the parameters are transferred. So trans resistance amplifier. Is it okay? I'm not drawing circuit for this and this because we have seen for one only, that is voltage control voltage source. Similarly the circuits you can see over there. Okay. And in any case you will connect the system. Your output will be always, or your feedback or your gain after feedback will be always A divided by 1 plus A beta. Why this plus? Because this is the negative feedback. Negative feedback. Okay. So in the negative feedback we have seen some properties of it. The effect of negative feedback. In the negative feedback, if I'm talking about the gain is always reduces. What about noise? Noise is reduced. What about distortion? Distortion is also reduces. Okay. What about stability? Stability of the system is always increases. Stability, bandwidth also increases in the negative feedback. Okay, so these are some advantages of negative feedback so for today's class it's enough. In the next class we'll see problems based on this negative feedback amplifiers, and we'll see various connection topology in the feedback amplifier. Okay, so we'll meet in the next class. Till then, take care and bye.